When the reaction is taken place between acid and base, that time salt and water will be formed. That overall reaction will be called it as neutralization. How usually we'll represent weak acid by Ha, weak base by BOH and salt by Ba. K plus and Cl minus, if not at all reacting with H plus and OH minus ions, obviously this concentration of H plus and OH minus will not change. Hello everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today I am going to start session 8 from the chapter Chemical Equilibrium. In the last session we have discussed about what is buffer solution and its types, pH of buffers, that is Henderson's equation, also buffer capacity. And these are the three concepts we have discussed in the previous session. In today's session we will discuss about salt hydrolysis, solubility product and also common ion effect on solubility of ionic salts. These are the three contents which we will discuss in today's session. First we will see what is salt hydrolysis. An areneous acid is a proton donor and an areneous base is a hydroxide ion donor. This concept we know from Arrhenius concept, that is acid is a proton donor and base is a hydroxide ion donor. This is H plus, this is OH minus ion donor. The reaction between equivalent amounts of acid and base to form salt and water is generally known as neutralization. When the reaction is taken place between acid and base, that time salt and water will be formed. That overall reaction will be called it as neutralization, because acid and base, when it both reacts, it will get neutralizes to form salt and water. It may imply that the resulting salt solution is always neutral, but salt solutions need not be necessarily neutral. After neutralization, what will be the salt will be formed? We will think that it will be neutral, but all the salt solution will not give us completely or necessarily neutral salts. Okay. Due to a phenomenon known as salt hydrolysis, the resulting solution may be acidic or basic also. Here, the phenomenon salt hydrolysis will come into the concept. Because of that salt hydrolysis, that salt solution may be acidic or basic also. Hence, we might consider hydrolysis as a reverse of neutralization. Okay. Because of this concept, it may be acidic or it may be basic. We will consider that hydrolysis is a reverse of neutralization. Depending on its strength, an acid may be considered as relatively weak or strength. This concept we know already. Depending on its strength, acid may be strong or weak. Similarly, bases may be considered as relatively weak or strong. Hence, salt can be classified as follows. In both the concept like acid or bases, depending on strength, it may be strong, also it may be weak also. Based on that, that salt is classified as follows. That is, salt of strong base and weak acid, salts of weak base and strong acid, salts of weak base and weak acid, salts of strong acid and strong base. These are the 4 types of salt. It has been classified. It is usual to represent a weak acid by Ha, weak base by BOH and a salt by Ba. How usually we will represent weak acid by Ha, weak base by BOH and salt by Ba. Next, hydrolysis of salt. The phenomenon in which the anion and the cation of a salt reacting with H plus and OH minus present in aqueous solution, forming respective acid and base, resulting in the formation of acidic or basic solution, is referred to as salt hydrolysis. What they are telling? In this phenomenon of hydrolysis of salt, what will happen? Anion and cation of a salt will react with H plus and OH minus in aqueous solution, forming respective acid and bases. Okay, salt with H plus and OH minus will form respective acid and base. Salts are 4 types. Salts of strong acids and strong bases. These are the 4 types we have seen in the previous slide, and with examples we will see. With strong acid and strong base means sodium chloride, potassium chloride, sodium nitrate, potassium sulfate, etc. Salts of strong acids and weak bases means ammonium chloride, ammonium nitrate, ammonium sulfate, etc. Salts of weak acid and strong base means sodium cyanate, sodium carbonate, sodium acetate and potassium acetate, etc. Salts of weak acid and weak base means ammonium acetate, ammonium cyanate, ammonium carbonate, etc. Usually wherever sodium is present, it will show strong base. Wherever ammonium is present, it will show weak base. So by like this you have to understand, you have to remember all the examples with respective salt. Salts of strong acid and strong base. Strong acid and strong bases. Consider for example potassium chloride, that is KCl, dissolved in water. The K plus and Cl minus ions that are formed do not have the tendency to react with H plus and OH minus. Usually potassium chloride means KCl. Here K plus and Cl minus ions will form, but that two ions do not have the capacity to react with H plus and OH minus ions of water. Consequently, there is no change in the concentration of H plus and OH minus ions also. K plus and Cl minus, if not at all reacting with H plus and OH minus ions, obviously this concentration of H plus and OH minus will not change. Thus, aqueous solutions of salts of strong acid and strong bases are neutral. That is pH equal to 7. What we have understood? If the salt after dissolving in water, if that ions, obviously it will get separate. If it is not reacting with H plus ions and OH minus ions from water, then the concentration of H plus ions and OH minus ions will not change. By that what we have to understand? From strong acid and strong base, whatever the salt will be formed, that salt will be neutral. That is, that pH will be equivalent to 7. Completely neutral salt. And we'll see another example, salts of strong acid and weak base. Consider for example ammonium chloride, NH4Cl. Here Cl minus ions reacts with H plus ions of water to form HCl, a strong acid. The NH4 plus ions reacts with OH minus of water to form ammonium hydroxide, which is a weak base. Since a strong acid and weak base are formed in the resulting of solution, concentration of H plus ions will be greater than concentration of OH minus ions, because acidity is more than basicity. Therefore, aqueous solutions of a strong acid and weak bases are acidic, that is pH is less than 7. Once again I am explaining, whenever salts of strong acid and weak bases we are observing, we are taking one example, ammonium chloride, that is a salt. It is dissolved in water. Obviously NH4 plus ions and Cl minus ions will liberate. That Cl minus ions will react with H plus ions of water, and NH4 plus ions will react with OH minus ions of water. Whenever H plus and Cl minus is reacting, there a strong acid HCl will form. Whenever NH4 plus and OH minus of water will react, then NH4OH, that is ammonium hydroxide, which is a weak base, will form. Okay, that time the concentration of acidic acid will increases than concentration of base. Then overall salt solution, what will happen? Acidic. So the pH will be less than 7. See here, NH4 ammonium chloride will liberate, water will also dissociate, then NH4 plus Cl minus with water, NH4OH plus Cl minus plus H plus. Next, salts of weak acid, strong base. Consider for example sodium acetate. Okay, CH3 COONA. This is sodium acetate dissolved in water. Obviously acetate ion react with H plus ions to form acetic acid, which is a weak acid. Na plus ions react with OH minus to form NaOH, which is a strong base. Since a weak acid and a strong base are formed in the resulting solution. Here, the concentration of base will be more than concentration of acid. Therefore, aqueous solutions of salt, of weak acids and strong bases are basic. Therefore, pH will be greater than 7. Once again, I am explaining. Sodium acetate will be dissolved in water, salt of weak acid and strong base. Here, acetate ion and sodium ion will get separate. Acetate ion will react with H plus ion to form weak acid, that is acetic acid, and sodium ion will react with OH minus ion, which will form strong base called sodium hydroxide. Then if we make a comparison, obviously the concentration of base will be greater than concentration of acid. Then salt will be basic. Then pH will be greater than 7. See, this is the reaction. This is sodium acetate. Here Na plus and acetate ion will form. Next, water will be liberated, H plus and OH minus ion. Next, acetate, sodium ion and water will form weak acid and strong base. Next, salts of weak acid and weak base. Consider for example ammonium acetate. Ammonium acetate is dissolved in water. It will form acetate ion and ammonium ion. Acetate ion will react with H plus ions to form acetic acid, which is a weak acid. Ammonium ion react with OH minus, which will form ammonium hydroxide. It is a weak base. Since a weak acid and weak base are formed in the resulting solution, H plus ions concentration of acid may be near equal to the concentration of OH minus ions. Therefore, aqueous solutions of salts of weak acid and strong base are almost neutral or slightly basic or slightly acidic depending upon the salt used. Here we have taken ammonium acetate. Here also when it is dissolved in water, ammonium ion and acetate ion will form, and acetate ion will react with H plus ion to form weak acid, that is acetic acid. Ammonium ion will react with OH minus to form ammonium hydroxide, which is a weak base. So after reacting with weak base and weak acid, obviously the concentration of acid and base, it will be almost 2 equal. So that salt may be slightly acidic, slightly basic or completely neutral. There is a 3 chances also. Usually it will be neutral only. Next, hydrolysis of salt. So here degree of hydrolysis constant of a salt. What they are checking? Strong base, weak acid. If it is strong base, basic salt can be expected. Here degree of hydrolysis x equal to root of Kw by C into Ka. Here dissociation constant also you can observe. Here Kh equal to Kw by Ka. pH will be equal to half into pKw plus pKa plus log C. See here strong acid and weak base, acidity will be there. X equal to root of Kw by Ckb, Kh equal to Kw by Kb, pH equal to half into pKw minus pKa minus log C. Weak acid, weak base almost neutral. Kw by Ka into Kb, Kh equal to Kw divided by Ka into Kb, pH equal to half of pKw plus pKa minus pKp. These are the formulas which will be used for numericals. Next, solubility product. Consider the saturated solution of sparingly soluble salt AB containing some undissolved salt. 2 simultaneous equilibria are possible in the solution. What they are telling? Take a saturated solution of sparingly soluble of salt AB. You have to take a saturated solution and little bit salt should be left without dissolving. AB, it will form aqueous solution and A plus and B minus. Applying the law of mass action to the ionic equilibria. This is equilibrium constant equal to concentration of product divided by concentration of reactant, where K is the dissociation constant of the electrolyte. Concentration of AB is a constant at constant temperature as dissolved AB is in equilibrium with the undissolved salt. Let concentration of A be equal to K dash, because this is undissolved, right? K into K dash equal to KSP, that is solubility product, equal to concentration of A into concentration of B, where KSP is the solubility product of the sparingly soluble salt. It is a constant at constant temperature. Solubility product of a salt is defined as its ionic product in a saturated solution at a given temperature. What they are telling? Ionic solubility product of salt is defined of its ionic product in a saturated solution at given temperature. There are several ionic compounds having such low solubilities that they could be considered as sparingly soluble or almost insoluble. Ionic compounds are hard, we know that, and it may be having low solubility constants or sparingly soluble capacity is there. At constant temperature at equilibrium, a reversible reaction takes place between the solid and its ions. Consider the saturated solution of silver chloride. It dissolves to a very small extent to form AgCl. It dissociates into ions as follows. Here silver chloride will get into aqueous solution and it will form Ag plus and Cl minus. Here AgCl in the aqueous medium is the solubility of silver chloride at a given temperature. For this equilibria, here concentration of product by concentration of reactant, dissociation constant of AgCl equal to concentration of Ag plus into concentration of Cl minus. Then solubility product of sparingly salt is Ag plus into Cl minus at given temperature. Every substance of low solubility is associated with the characteristic Ksp, which depends upon the nature of substance and the temperature. So, dissociation constant of solubility product of a given substance is a constant at constant temperature and changes with the change in temperature, which is solid at 18 degree Celsius. Okay, usually at given temperature it will be constant, but at the temperature of 18 degree Celsius it may be changed. Here compound lead sulfide 3.4 into 10 to the power of minus 28, copper sulfide 8.5 into 10 to the power of minus 45, mercury sulfide 4.1 into 10 to the power of minus 54, manganese sulfide 2.2 into 10 to the power of minus 16. This is some of the compound. Ionic compounds are any compounds which is sparingly soluble with its solubility product. The solubilities of group 2 sulfides are much smaller than solubilities of group 4 sulfides. Sparingly soluble salts can be classified as AB, AB2, A2B, A2B and AB3 types. Consider a very general case of the AXBY. This is number of moles which we have used and this is coefficients, and this common expression takes various forms depending upon the values of X and Y. Valencies of B and A respectively. Here AB type, how it will be dissolved? A plus, B minus. For that example, silver chloride giving Ag plus and Cl minus and barium sulfate, Ba2 plus and sulfate. And Ab2 type, A2 plus plus 2B minus, example lead iodide and calcium fluoride. Next A2B type, silver chromate, A2B3 type, antimony sulfide and AB3 type, ferric hydroxide. See everywhere the solubility product has been written with its concentration, with the X value and with its coefficient. Next, relationship between solubility and solubility product. Solubility product expression. Consider a saturated solution of barium sulfate, which is the electrolyte of the type AB. Barium sulfate which form barium 2 plus plus sulfate 2 minus. Let the solubility of barium sulfate be S into mole per dm cube, since each barium sulfate molecule that dissolves produces one barium 2 plus ion and one sulfate ion. Here concentration of barium 2 plus ion will be equal to S into mole per dm cube and concentration of sulfate ion will be equal to S into mole per dm cube. Obviously K, that is solubility product, will be concentration of barium 2 plus into concentration of sulfate. So S into S will be S square, Ksp will be equal to S2 or S will be equal to cube root of Ksp by 4. Another example, consider a saturated solution of silver chromate, that is AB2 or A2B type. Here also silver chromate will form Ag1 plus and chromate 2 minus. For Ag plus 2S mole Dm cube will takes place, and for chromate S mole Dm cube. Okay, 2S square into S will form. These two steps are common steps which we have seen before derivation. Equal to 2 into 2 4s cube, or s will be equal to cube root of Ksp by 4. This is about relationship between solubility and solubility product. Next, common ion effect on solubility of ionic salts. When a saturated solution of sodium chloride is taken and hydrochloric gas is passed through it, sodium chloride is precipitated due to increased concentration of chloride ions available from the dissociation of HCl. Sodium chloride thus obtained is of very high purity, and impurities like sodium and magnesium sulfates can be removed. What they are telling? When sodium chloride is reacting with hydrogen chloride, obviously the chloride concentration will increase, and sodium chloride thus obtained is of very high purity. Whatever we'll get, that sodium chloride will be high purities like sodium and magnesium sulfates can be removed. Common ion effect is also used for complete precipitation of particular ion as its sparingly soluble salt with very low value of solubility product. Which is having more solubility product can detect that salt of low solubility product. This method is also useful to precipitate silver ion as silver chloride, ferric ion as ferric hydroxide, and barium ion as its sulfate for quantitative estimations. How it can form precipitation of a low solubility salt from high solubility salt. The solubility of salts of weak acids like phosphates increases at lower pH. Because at lower pH the concentration of anion decreases due to protonation. This is in turn increases the solubility of the salt such that Ksp will be equivalent to Qsp. In the salts of weak acid like phosphates, it increases the concentration of lower pH. Their concentration of anion will be decreases, and inversely it will increase the solubility product of salt such that Ksp will be equivalent to Qsp. Here Ksp equivalent to concentration of M plus into X minus, that is Hx will be given H plus X minus. You know, K equal to concentration of product by reactant. Taking into left hand side, concentration of X minus by Hx equal to Ka by H plus. Taking inverse on both the sides and adding 1, Hx by X minus plus 1, H plus by Ka plus 1. Okay. And you have to cross multiply Hx plus X minus 1, X minus by X minus equal to concentration of H plus Ka by Ka. Now again taking inverse, we have to inverse and we will get F. F decreases as pH decreases. If S is the solubility of the salt at a given pH, then Ksp will be equal to concentration of S into concentration of Fs, which will be equal to S square into Ka by Ka plus concentration of H plus, and which will shows S equal to Ksp into H plus Ka divided by Ka. This square will be considered as half power. Thus solubility increases with increase in concentration of acid or decrease in pH. Whenever increase in acidity will takes place, solubility will be increases. Next, solubility product and precipitation of electrolyte. Solubility product of a sparingly soluble salt at a given temperature is its ionic product only in saturated solution. You know about saturated solution, you know about solubility product. So, solubility product of a sparingly soluble salt at a given temperature is its own product only in saturated solution. In an unsaturated solution, ionic product will be less than solubility product, and so more salt will dissolve. If ionic product is more than solubility product, the equilibrium is shifted to the left and more undissociated salt will be formed. But the solution cannot hold more salt since it is already saturated and the excess salt gets precipitated. Hence, we have three situations. What they are telling? If we have taken salt, any salt which is dissolved in water, after the saturation point, if you add more salt in same water, it will not get dissolved. So, for that, three situations have been taken. If ionic product is less than solubility product, unsaturation and more salt will dissolve. If ionic product will be equivalent to solubility product, saturated solution will form, means equal. Solvent is also equal, solute is also equal. Neither dissolution nor precipitation of the salt occurs. If ionic product more than solubility product, supersaturation, precipitation of the salt occurs. This principle is used in qualitative and quantitative analysis of the metallic salt. If ionic product is less than solubility product, no saturation or unsaturation. Ionic product equivalent to solubility product, complete saturation will take place. Ionic product is more than solubility product, supersaturation or precipitation will take place. This is general concept with three situations. Applications of solubility product principles. Solubility product principle is used in many industrial processes, qualitative analysis and quantitative analysis. This solubility you may check in inorganic salt testing also in your laboratories. First you will check with solubility test. And industrial applications, preparation of table salt. Common salt contains several water insoluble and soluble impurities. A saturated solution of common salt is prepared. Insoluble impurities are filtered and removed. HCl gas is passed through this saturated solution. The ionic product of NaCl exceeds its solubility product. Increase in and pure NaCl precipitates out. Why they are using in preparation of table salt or any purification technique means whatever the impurities may get dissolved in water, the impurities will be removed and it will be filtered off. The remaining whatever the salt will be present, that will be purified form of salt. Usually we will use in sodium chloride. Next, salting out soap. Soap is sodium salt of higher fatty acids. When fats and oils are digested with sodium hydroxide, soap is formed. You know how soap will be formed. Sodium chloride is added to the saturated solution of soap. Whatever the saturated solution of soap will be there, here sodium chloride will be added. Na plus ions increases ionic product of soap so as to overcome its solubility product. Soap is precipitated. This is called salting out of soap. This is very much important application of solubility product. Next, manufacture of sodium bicarbonate, that is Solvay soda ammonia process. How the sodium bicarbonate will be produced? Brine solution is first saturated with ammonia and then with carbon dioxide. Brine solution means sodium chloride solution. The following equilibrium exists in the solution. Ammonium hydroxide treating with carbon dioxide, ammonium bicarbonate will form. Then ammonium bicarbonate treating with sodium chloride, that is brine solution. Sodium bicarbonate with ammonium chloride will form. Here solubility product of sodium bicarbonate is much less than solubility products of ammonium bicarbonate and ammonium chloride. Hence, sodium bicarbonate gets precipitated. Next, qualitative analysis. Precipitations of group 2 and 4 sulfides. The second group reagent is H2S, that is hydrogen sulfide in presence of hydrochloric acid. H2S is a weak electrolyte and its ionization is suppressed by the H plus ions of the strong electrolyte HCl. Hence, in acidic medium, S-2 concentration will be low. Thus, group 2 metallic sulfides with very low solubility products get precipitated in acidic medium and group 4 sulfides stay in the solution. Here group 4 stay in the solution and here metal sulfide. Here solubility product at 25 degrees Celsius. This is group 4 metallic sulfide and solubility product at 25 degrees Celsius. Bismuth, mercury, copper, lead, here cobalt, nickel, zinc, manganese with its solubility product. Solubility product of cadmium sulfide is slightly higher and sometimes it does not precipitate in concentrated HCl solution. To precipitate cadmium sulfide, the solution is generally diluted to favor the dissociation of H2S. After removing of H2S, the cadmium sulfide will form. Group 4 reagent is H2S in presence of ammonium hydroxide and ammonium chloride. The hydroxide ion neutralizes the proton from hydrogen sulfide and the dissociation of H2S is favored. This increases the concentration of S2 minus, hence group 4 metallic sulfides are precipitated. If the precipitations of group 2 sulfides are missed in the analysis, the same will be precipitated along with group 4 metal sulfides. These things you know in the salt analysis. If one group has been missed, then automatically in the next group you will be finding out these radicals. Here generally if you miss a group second, it will be available in group 4. Next, precipitation of group 3 hydroxides. The group 3 reagent is ammonium hydroxide in presence of ammonium chloride. Ammonium hydroxide is a weak electrolyte. It undergoes partial dissociation as NH4, OH will be NH4 plus and OH minus. NH4Cl is a strong electrolyte. It ionizes to give NH4 plus and Cl minus. The ionization of the NH4OH is suppressed by the ammonium ions produced by NH4Cl due to common ion effect. There, precipitation of group 2 and group 4 we have seen by HCl and H2S. Here precipitation of group 3 hydroxide by using ammonium hydroxide and ammonium chloride. One is weak electrolyte, another one is strong electrolyte, and it is suppressed due to the common ion effect. At the low concentration of OH minus, only hydroxides of group 3 cations with very low solubility product get precipitated. Hydroxides of nickel, cobalt, zinc, magnesium are not precipitated since their solubility product is high. This completes your chemical equilibrium chapter. I hope you have understood completely whatever I have taught today also, like solubility product and its applications. We'll meet in the next new chapter. Till that, thank you.